Hello everyone, I'm Hangzhu from Johns Hopkins University. Today I'm glad to present our work, NetVRM, Virtual Register Memory for Programmable Networks. This is a joint work with people at Johns Hopkins University, New York University, Microsoft Research, and Peking University. The programmable networks have been changing how we design, build, and manage computer networks. And there are two broad types of objects provided by commodity programmable switch on the data plane. The first one is the stateless objects, whose lifespan is within one single packet. These objects cannot preserve state between packets. Some examples are metadata packet headers. The other type is the stateful objects. The state is preserved between packets in these objects, such as counters, tables, counters, meters, and registers. Among them, registers enable a new class of rack stateful applications, which utilize the on-chip register memory to realize various functionalities. Then I'd like to introduce the case of dynamic allocation for register memory. Someone may ask, why we need a dynamic register memory allocation? The first one is a necessity. Register memory on programmable switches is fundamentally limited by the hardware. For example, there's only a few metabits register memory per stage on Intel to Fino switch. Besides that, modern cloud service providers usually serve multiple tenants concurrently and allow them to run different network applications dynamically. So a mechanism for register memory allocation is necessary for these concurrent rack stateful applications. The second is the potential benefits of dynamic register memory allocation, which arise from the diminishing return. So what is diminishing return? This figure shows the utility curves of net cache with different skilled workload. So net cache uses register memory to maintain hot key value pairs on the data plane to serve a request upon a cache hit. So take the green line with zip 0.9 as an example. We only need 768 register slots to increase the utility from 0.28 to 0.36. But if we want to increase the utility further by 0.1, we need extra more than 3,000 register slots. So we say the diminishing return means the benefit of additional memory decreases with the amount of allocated memory. And our observation is that such diminishing returns are common across many different rack stateful applications, including the different network measurement applications that store the flow records and evict the existing entries from the data plane upon hash collisions. Such diminishing return provides us the opportunity to maximize the resource multiplexing benefits by efficiently arbitrating the memory allocation between these concurrent applications. Recently, several existing works have explored how to support multiple applications on our programmable switch. These solutions fail to meet the requirements of dynamic register memory allocation because of at least one of the three limitations below. The first one is the static binding between register memory and the application. Some of the existing work merge multiple applications in compilation time, such as p4 weather. To change the memory allocation, you need to modify, recompile, and reload the p4 program. Second, they usually ignore the practical hardware constraints. They realize their approaches in software environment, such as DPDK, behavior model. One example is Hyper4. At last, most of the existing work focus on one single switch. They are not doing network-wide dynamic allocation. So to realize the dynamic register memory allocation, there are three main challenges. The first is how to enable online allocation, which can be addressed by our virtual register memory design. The second is how to modify the P4 programs to realize the virtual register memory. We introduce an extension of P4, P4VRM, and provide the P4VRM compiler to simplify the data plane program development. The last one is how to maximize multiplexing benefits. We design a network-wide dynamic allocation algorithm to handle this. Putting the three components together, we have our design, NetVRM. NetVRM is the first approach that realizes dynamic register memory allocation online without recompiling and reloading the data plane program. First, we will talk about the virtual register memory design. The virtual memory is basically realized by the two-page table design. The page table in the data plane matches on the application ID and identifies the location and the size of the application's memory region by setting two metadata fields, the offset and the size. The other one is on the control plane for NetVRM to query and update the virtual memory of applications. We also maintain counter record to compute real-time memory hit ratios, which are used for dynamic memory allocation. So how a virtual address, VA, is translated into a physical address, PA. The physical address consists of two parts, the array index, which can be calculated as VA divided by size, and the slot index, which can be calculated as VA mod size plus offset. We give a simple example here. The green partition shows a memory region for an application, and the numbers inside the slots is a virtual address, starting from 0 to 7. We can see the size is 2 and the offset is 1. So given VA equals 5, we can compute the PA to be 2 based on the translation formula. So we can locate the physical slot as the arrow points to. The second component is the dynamic memory allocation. In principle, NetVRM supports any memory allocation algorithm given the virtual memory design. Our default objective is to maximize the number of applications which the utility targets can be satisfied. And the constraints are to ensure the sum of allocated register memory on each switch does not exceed its memory size. At first, we'd like to identify the applications that can benefit from the dynamic resource allocation. Basically, we classify the reg stateful applications into elastic applications and inelastic applications. Elastic applications can work with a variable amount of register memory, and it overcomes insufficient register memory with some fallback mechanism. One example is net cache. And inelastic applications require a fixed amount of register memory. It cannot work with less. NetVRM supports both types, but only elastic applications can benefit from NetVRM's dynamic memory allocation. There are three challenges for dynamic resource allocation between elastic applications. The first challenge is how to find a proper definition of application utility. NetVRM uses memory hit ratio as a default utility. The memory hit ratio is the ratio of packets directly processed by the register memory in the switch. As the figure shows, we have n packets, and m packets are processed by the register memory. Then n minus m packets will turn to the fallback mechanism, such as a backend server. Then the hit ratio can be calculated as n divided by n. There are three main reasons why we use memory hit ratio by default. First is application agnostic. For example, we do not have to compare the accuracy of a heavy hitter detection with the throughput of net cache. Second, Our observation is that for elastic applications, a register memory miss in packet processing usually affects the application level performance, such as the extra latency to process a packet with a fallback mechanism. And at last, the hit ratio can be computed online by tracking counters. The second challenge is that the utility functions of the applications are unknown and dynamic. And our solution is an online utility curve estimation. For applications that have better utility than the target, we estimate overmem, which is the amount of memory that can be moved from the application. For applications that have not reached their utility targets, we calculate the undermem, which is the amount of memory to be added to the application. As the figure and the formula shows, the utility function is approximated with a polynomial function that intersects the origin. We set the CF to be larger than 1 to compensate the concavity. The third challenge is the multiple paths of an application. Our solution is to do network-wide register memory allocation. At a high level, it contains 2 steps. The first step is to decompose overmem and undermem to multiple paths. The second step is to move the memory from over-provisioned applications to under-provisioned applications. More details of the algorithm can be found in our paper. The third component is P4VRM, an extension to P4. To use a P4VRM compiler, developers extend the P4 programs to P4VRM programs in the first step by tagging the declarations related to a register array that you want to virtualize. In step 2, the compiler takes multiple P4VRM programs as input and outputs one merged P4 program with virtual memory abstraction and online utility measurement, together with the C++ APIs to configure the virtual memory efficiently from the control plane. We built a NetVRM prototype on a 6.5 Tbps Intel to FinO switch and emulated 4 switches with 4 independent pipelines. Our P4VRM compiler is built on FlexPython. We evaluate our prototype in 2 scales. In this talk, we will talk about the control loop delay, the generality, and the impact of allocation epochs. This figure shows a breakdown of the control loop delay, which is the time to complete a virtual memory allocation with different number of concurrent applications. We can see NetVRM can complete one memory allocation at most in around 10 milliseconds. For the 4 parts, the fetch represents the time of fetching counters, calc is the time of calculating online utility and the new memory allocation plan, reconfig is the time of configuring the page table, runtime is the runtime overhead for resetting the state. The time of reconfig dominates the control loop delay because of the intensive updates to the data plan. In the generality experiment, each application has traffic from 4 switches independently, and we use satisfaction ratio as a performance metric. Satisfaction ratio is defined as a fraction of a network application's lifetime that it meets its utility target. The alternatives are equal all and equal active. Equal all statically assigns an equal amount of memory to all applications, no matter it's active or not. Equal active only assigns an equal amount of register memory to active instance. The figure shows NetVRM outperforms the alternatives on both the mean and the 5% tail satisfaction ratio among the 256 application instances, and is general to different network application types, including the heavy hitter detection, the newly open TCP connection detection, the super spreader detection, and the sketch-based heavy hitter detection. In this figure, we vary the allocation epochs from 2 seconds to 16 seconds. The results show that a shorter allocation epoch leads to a better performance, both in mean and the 5 percentile. To conclude, NetVRM is a network management system to support dynamic register memory sharing between multiple concurrent applications on a programmable network. It has a virtual register memory, which enables online register memory sharing, and it dynamically allocates memory for better resource efficiency. It also provides P4VRM to make the program development with virtual register memory easier. That's all, and thank you.